Okay, lesson 7, algebra 2. We're now talking about secant and what's called the cofunctions. So far we've learned about sine, cosine, and tangent. Now we're going to move into secant and cosecant and cotangent. Very exciting. First of all, let's just look at our opening exercise. This is a review of what we've done the past few lessons. I have my unit circle and a terminal ray and an initial ray. Let's try to remind ourselves, find the lengths of each segment below in terms of the value of a trigonometric function. So OQ just goes from here to here, and we've done SOHCAHTOA. I just reviewed that last lesson too. Its sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Since our hypotenuse is 1, segment OQ should be just plain old cosine theta, because cosine is adjacent to theta. PQ is right here, and that's the opposite of theta, so that would be your sine function. And then RS would be right here, which is your tangent, which is also sine over cosine. Cool? Next. Okay, let's just go through a few new things. This is what we're learning today. Since there are ways to calculate lengths for nearly every segment line in the diagram, using the length of the radius or the cosine, the sine, and the tangent, it makes sense to find the length of OR. Hold on. So we were talking about finding the length of OR, which I just wanted a picture so we all knew what I was talking about. It's the terminal ray from the center all the way out to the tangent. So the line segment on the terminal ray that intersects the tangent line, that's what I just said. What do you call, now we're up here, what do you call a line that intersects a circle at more than one point? It's called the secant line. Remember I drew you guys a circle, okay, I intersected at 2 points, it's called the secant. Granted, right now we're talking about the unit circle and the coordinate plane, so I should draw something slightly more technical. That's a beautiful line. So we have a secant line. In lesson 6, we saw that RS, right here, is your tangent of theta, where RS lies on the line tangent to the unit circle. And that helped us to explain how this trigonometric function got its name. Let's introduce a new function, secant theta. The secant of theta is the length of OR. O to R, since this segment is on the secant line that contains the terminal ray. Secant line hits the circle at 1, 2 points. The secant of theta is secant theta is OR. That is what we're going to remember right now. Secant theta equals OR. Cool? Okay, let's use that in an example. Okay, let's try example 1. Use similar triangles to find the value of secant theta in terms of one other trigonometric function. I copied this back into our slide. Let me highlight this and then I'll delete it. So by similar triangles, I have one triangle and another triangle. We know they're similar because of the A or the angle-angle similarity theorem. When two sets of triangles have two angles that are congruent, then the triangles are similar, which means the sides are going to be proportional. Okay, you guys learned that in geometry. Let's erase all of this. Okay, so if we look at similar triangles, I can say that OR, which is a side of the larger triangle, over OS, I'm sticking with one triangle, is equal to OP over OQ. Let's highlight that. So I did OR, big triangle, over OS, big triangle, is equal to OP over OQ. Okay, little triangle, little triangle. Okay, so we know that OR is secant theta, and OS is 1, and that is equal to OP, which is 1, over OQ, and OQ is cosine theta. Okay, we did that on our opening exercise, right? We did all of that. Cool. Therefore, if I solve for secant theta, I get 1 over cosine theta. This right here is finding the value of secant theta in terms of one other trigonometric function. Cool? Okay, let's get into exercise 1. The definition of secant function is offered below. Answer the questions to better understand this definition and the domain and range of this function. That's going to be important for us to remember. Be prepared to discuss your responses with others in your class. Yes, others in your class. All right, let theta be any real number. In the Cartesian plane, rotate the non-negative x-axis by theta degrees about the origin. Intersect this new ray with the unit circle to get a point, x theta, y theta. If x theta is not equal to 0, then the value of secant is 1 over x theta. Otherwise, secant theta is undefined. If x equals 0, then it's undefined. In terms of the cosine function, secant theta equals 1 over cosine theta. This right here is going to be our working definition. Okay, this is what I still use to this day. But cosine theta cannot equal 0. Okay? So we know that secant theta equals 1 over cosine theta. All right, so first of all, what is the domain of the secant function? The domain is all real numbers. But theta cannot equal 90 or any combination of 90. Okay, theta cannot be 90 or 270 or back up to 90. I mean, I can't stay here, can't go down there, or anywhere else. So this would be the 180 times k. Every time I hit the y-axis, I've gone another 180. So that's why it has to be an integer, because any whole number times 180 plus 90 is what theta cannot equal. The domains of the secant and tangent functions are the same. Why? Well, it makes sense. Both the tangent, both the tangent and secant functions can be written as rational expressions. With cosine theta in the denominator. And cosine theta is my x value of an ordered pair. So at 90 degrees, x is 0, can't divide by 0. At 270 degrees, x is 0, can't divide by 0. And then I go back up, can't divide by 0, can't divide by 0, etc., etc., etc. So that's really why they're the same, since tangent of theta equals sine theta over cosine theta, x can't be 0, and then secant theta equals 1 over cosine theta. x can't be 0. So we have restricted values in their domains because of the denominator, and the denominator cannot be 0. What is the range of the secant function? Okay, secant theta equals 1 over cosine theta. Negative 1, let's see where this leads us. Cosine theta, my range is my output. And that can be anywhere from negative 1 to positive 1. And that works. But to relate that back to secant, where secant theta equals 1 over cosine theta, secant theta is going to be either greater than or equal to 1 or less than or equal to negative 1. Okay, so the range of secant theta can go anywhere from negative infinity to negative 1. Oops. Union with 1 to infinity. So that right there would be our range. Our domain is on the previous page. The range of cosine is right here. Is the secant function a periodic function? Oops, I'm in red. Yes, it's periodic, and it can go all the way from 0 to 360, one period. So it repeats itself every 360 degrees. Oops. Okay, let's review a few things just to make sure we're all on the same page. What are the values of secant theta when the terminal ray is horizontal? When the terminal ray is horizontal, it's going to coincide with the positive or negative x-axis. Okay, this would be horizontal. So the values would be a 1 or a negative 1. Okay, I'm over here or over there. Secant theta would be 1 over 1, which is 1. And then the other side, secant theta would be 1 over negative 1, which is negative 1. Okay, when the terminal ray is vertical, that's when we're undefined, right? So let's do that. Here we go. So when secant theta, when the terminal ray is vertical, the x-coordinate of point P is 0. So secant theta equals 1 over 0, which is undefined, or secant theta is negative 1 over 0, which is, again, undefined. Okay, let's take a second to review this. It's sort of a summary of domains. For tangent theta, x can't equal 90 or any combination of 90. You know, if we take theta and we go up and we hit 90 degrees, it's the y-axis, which is where x equals 0. Go down and hit the negative y-axis, I'm still at x equals 0. And then every single time I hit the y-axis. That's why k is an integer. So this would be 90, and then 270, 450, etc. So every time I hit the y-axis, my tangent theta is undefined. That is the same for secant, because secant is 1 over cosine, which is 1 over your x value. Your domain cannot be theta is 90 or any combination of 90 plus 180 times k. Cosecant, it just can't be on the x-axis. That's where we are undefined, right? Because y, it's divisible by y, and when I hit the x-axis, my y value is 0. Same for cotangent. All right, let's look at something else. I have exercise 2. In the diagram, the horizontal blue line is the tangent to the unit circle at 0, 1. So our tangent has moved. How does this diagram compare to the one given in the opening exercises? It's basically the same. In the opening exercises, my tangent was, that should be tangent, right there, just make the line thicker, right? There's my terminal ray, and I have R, let's see, this was Q, that's P. I can't remember what this one is named. It might still be S, and that is your origin. So that's the difference. It's basically the same diagram with different angles and lengths marked. We can consider a rotation through beta degrees measured clockwise from the y-axis. So we're doing clockwise. So beta clockwise from the y-axis instead of a rotation through theta degrees measured counterclockwise from the x-axis. It's essentially a reflection of the diagram from the opening exercise across the line y equals x. So we just reflected it. What is the relationship between beta and theta? Let's see. We have, I believe, beta plus theta is 90 degrees, which you can see in the diagram pretty easy. Which segment in the figure has a length sine theta? Let's see, sine theta would be OU if you go back and look at it, and then cosine theta would be, oh wait, yeah, sine theta is OU, just looking at that diagram again, and cosine theta is UP. What segment in the figure has the length sine beta? That would be UP, and we'll see how we're just trading places. OU is cosine beta. And how can you write sine theta and cosine theta in terms of trigonometric functions? And then we have cosine theta equals, that's messy, sine beta. There you go. Example 2. Use similar triangles to show that if theta plus beta equals 90 degrees, then secant beta equals 1 over sine theta. Tangent beta equals 1 over tangent theta. Okay, so the horizontal blue line is the tangent to the circle at ordered pair 1, 0. If we look at the triangles OPU, let's see if I can highlight those. OPU and ORT. There we have our similar triangles. It'll be pretty easy to set up. I have OR over OP. I just did blue over red equals TR over UP. And the last slide, we assigned a few trigonometric functions to those. OR was secant beta, and OP was 1. TR is tangent beta, and looking back, UP is cosine theta. Okay? Since cosine theta equals sine beta, which we just wrote, and so cosine theta is sine beta, and sine theta equals cosine beta. We can write secant beta equals sine beta over cosine beta, which is tangent, over cosine theta. All I did so far was change tangent beta into sine beta over cosine beta, and I kept cosine theta the same. A second ago I just restated what we said in the last slide, that cosine theta equals sine beta and sine theta equals cosine beta. I'm going to use that right now, right over here. Secant beta equals sine beta equals cosine theta. Just switching this out for this one. And then cosine beta equals sine theta. Switching this one out for that one right there. All over cosine theta, which means that these are going to cancel out, and secant beta equals 1 over sine theta. That's what we were going for, right? Sort of messy. If two angles are complements with measures beta and theta as shown in the diagram, use similar triangles to show that, this is what we said we're going to do, tangent beta equals 1 over tangent theta. So let me get that diagram over here again. Hold on. So here we're going to look at triangles OPU again and triangle ORT. We're looking at similar triangles. And that shows us that we have RT, which is that horizontal one over OT, RT over OT. So we're going the blue triangle. RT over OT is going to be equal to PU over OU. RT we know is tangent beta, OT is 1, UP we know is cosine theta, and OU is sine theta. We know that tangent theta is sine over cosine. Let me write that down. We know tangent theta equals sine theta over cosine theta. So 1 over tangent theta equals cosine theta over sine theta, which I'm going to take back over here, right? So I can say that tangent beta equals 1 over tangent theta because of substitution. Right here, I just substituted it, and there we go. Phew. Definitions of the cosecant and cotangent functions are offered below. Answer the questions to better understand the definitions and the domains and ranges of these functions. Be prepared to discuss your responses with others, yada, yada, yada. We'll talk about it tomorrow if you have questions. What we see is cosecant is 1 over y theta, which is going to be 1 over sine theta. And cotangent is x over y, which is equal 1 over tangent theta. Okay? The secant, cosecant, and cotangent functions are often referred to as reciprocal functions because we flip them over. Cosecant, like I just said, is 1 over sine, so it's the reciprocal. Secant, I should put the theta in there. Secant theta is 1 over cosine theta, the reciprocal. And cotangent theta is 1 over tangent theta, which is the reciprocal. Okay? Why are the domains of these functions restricted? Same reason as everything is restricted. We can't divide by 0. And because we can't divide by 0, anything that would give us a 0 in the denominator would be a restriction. The domains of the cosecant and cotangent functions are the same. Why? Well, cosecant theta is 1 over sine, And then cotangent theta is 1 over tangent theta, which is cosine over sine. So right here, it's the same because if sine was 0, then it would be undefined, which is not allowed. What is the range of the cosecant function, and how is this range related to the range of the sine function? Well, first of all, we've learned in the past that the sine function has the range -1 to 1, so the cosecant is going to have sort of the flip of that range. The two ranges only intersect, I'll write that down here. The two ranges only intersect at -1 and 1. What is the range of the cotangent function? How is the range related to the range of the tangent function? The range of the cotangent function is all real numbers. And that's the same as the range of the tangent function. The tangent function has a range of all real numbers. So, to summarize everything, let theta be any real number. In the Cartesian plane, rotate the initial ray by theta degrees about the origin, intersect the resulting terminal ray with the unit circle to get a point x theta, y theta. And we'll get all of our formulas for the new ones and our values. Actually, let me include something else. Values for the other ones. And then we have our domain right here. Is where we are defined, okay, where we're not undefined. Cool. All right, we'll do our problem set tomorrow, and we'll be looking at our unit circle just a little bit further.